Hi, I'm Zor. Welcome to Unizor Education. We continue talking about spheres, and today's topic is a spherical cap. Well, let me just go back, I don't know, 500, 600, 1,000 years ago, and let's imagine some architect who wanted to create a beautiful cathedral. Well, you know that cathedrals usually have a dome on the top of it, right? So, obvious question is, how much material should I use for this dome? And probably there are some other considerations which require some calculations related to surface area of the dome and maybe its volume as well. So today we will talk about spherical dome and its volume, and in the next lecture we will talk about the surface area. Okay, so first of all, what is a spherical dome? Spherical cap, actually. Dome is just top of it. So if you have a sphere and you cut it with a plane which intersects, as we know from the previous lecture, along a circle, so the top which is cut by this plane, in this case the top part, this is a spherical cap, and surface, the top part of it, is called a dome, and the flat bottom is a base of a cap. So our task today is to calculate its volume. All right. First of all, how can we define this particular spherical cap? Which parameters should we use? Well, obviously we need to define the sphere, and that's the radius which defines it. And also another very important characteristic which is actually characterizes the cap itself is its height. Now, its height is basically the length of the longest perpendicular from the surface, from the dome of the cap down to its base. So if you will just take some perpendiculars, then the longest is the height, and that is h. So the height or altitude of the cap and the radius of the sphere from which this cap is cut are two parameters which would define our cap. Now, in our cases, we will always consider when h is not more than r. Why? Because look at this. I mean, if you increase the height up to the r, it will be half of the sphere. If the h is greater than r, then it's basically the top part. This part would be our cap when h is greater than r. And we don't really want to consider it because it gives some kind of difficulties. It's always better to consider the smaller part whenever the plane cuts this, the sphere. And the smaller part always has this characteristic, and that's what we will consider as a true spherical cap. So in a true spherical cap, we always consider the height to be smaller than the radius of the sphere. Now, let's talk about which exactly piece of this geometry represents the h, represents the height of the cap. Well, let's consider that we have some point on the surface of the dome of the cap from which perpendicular down to the base is the longest. So what can we do about this? Well, let's draw a perpendicular from the center to the plane which cuts the sphere. Now, we know from the previous lecture that this perpendicular falls into the center of a sphere, right? So let's consider some point here from which perpendicular down is the longest. Well, these are two perpendiculars, so they're parallel lines, perpendiculars to the plane, right? So we can cut another plane through these two perpendiculars. So what we will have as a result of this cut? Well, the plane goes through the center, so we will have from the whole circle from the whole sphere we will have a circle, right? And also it will cut along some line from here to here, right? These are the lines which belong to the plane, and when we cut, it will be in our cutting plane, right? So this is a straight line. So from this is the point on the dome from which we draw the perpendicular. So that would be the case, basically, right? This is the line. So this line would be this. Now, obvious from the plane geometry that only the point which has a perpendicular projecting to the center of this segment would be the longest. That's very easy to prove from the plane geometry case, and you obviously are welcome to do it yourself, but it's really very easy because of what? How can we compare it? Well, because if you add it to this, for instance, if this is a diameter, this is the radius, and this is smaller than the radius, right? Because the radius is hypotenuse, and this is the catetus. So that's why adding two equal parts will give this is smaller than this. So initial, same thing, smaller. That's easy. So what I'm actually talking right now about is that it's the top of the dome, the one which actually is a continuation of this radius, is the point from which the distance to the base is the biggest, the longest. So whenever I'm talking about h, I'm always considering that we have a radius from the center perpendicular to the plane which cuts the sphere, and wherever this radius ends, that's the point from which this distance is the greatest, and that's actually the h. That's the height of the spherical cap. All right. Okay, so we've done that. So this perpendicular to the plane is actually where the height is located, and now we can talk about volume. For this I need a slightly bigger. So what I will do is I will have something like this as my sphere. Now this is my perpendicular to the plane. So this is my plane, and on the top is my cap. Alright, I will do exactly the same kind of technique with calculating the volume of this as I used when I was calculating the volume of the sphere, which means I will divide this piece, I will call this is A0 and this is A capital N, into n equal parts. So this is h, right? This is h. And the whole thing, so h is A0AN, and R is A0O. From A0 to O is radius. From A0 to N, AN is height h. And these are points which I will call A1, A2, etc. Now, now I will cut the plane through each of these points, and I will replace this spherical cap with a set of cylinders stacked on each other. Okay? So, now, and that's where my calculations cannot really be qualified as strictly rigorous, because what I'm going to do is I'm going to calculate the sum of these volumes, sum of the volumes of these cylinders, and I will check what's the limit of this when the number of cylinders goes to infinity. And now I'm claiming, basically without any proof, and that's where non-rigorousness actually is. I'm claiming that this would be, in the limit, that would be the volume of this spherical cap. Now, the rigorous proof actually is required if you want to do it according to the letter of the law, and that's not a very easy thing to do, and it's definitely beyond the scope of the course. So right now I'm just asking you to rely on your intuitive understanding that as we are making these number of these cylinders greater and greater, they are closer and closer approximate the spherical cap. So right now my purpose is strictly technical. Alright, so if I want to calculate the volume of the cylinder number K, so somewhere here I have AK. So what's the volume of the cylinder? Now the height of each cylinder is very easy. Height of each cylinder is h divided by n, right? Because I divided this piece into n equal parts, right? So that's easy. Now the area of the base of this cylinder number K is basically the radius of, well, it is basically pi and the radius square, and the radius is the distance from the AK to the end of the sphere. So let me just go into a plane geometry right now, because that's really a plane geometry problem. So you have a circle, and you have, this is your height, this is your AK, and I want to know this radius of a circle on the level of AK. Well, that's a Pythagorean theorem, right? So this piece is R R minus this piece. Now if this is AK, it means that there are K in front of it. H1 is H divided by N little segment, so this piece is equal to H times K divided by N, right? So if I will subtract it from R minus this piece, that gives me this catetus, and the hypotenuse is equal to R. So by Pythagorean theorem I can calculate this. So it would be R square minus this square. That would be the square of this catetus. And the area would be, obviously, VK would be equal to, that's the volume, that's the volume, and its multiplication of area, which is pi and this square, right? So pi R square minus R minus HK divided by N square times the height of the cylinder. So that's my that's my volume of the case cylinder on this stack. Now what I have to do now is I have to summarize it by k from 1 to n, right? And take a limit as n goes to infinity. So I perfectly understand it, and the problem is not to make any mistakes because it's kind of complicated calculation. So I have written actually a couple of intermediate results, so I hope I will just do fine. But anyway, let me first simplify it a little bit. Equals to, so pi h divided by n, and what do I have here? R square and minus r square would cancel out, then minus rhk, that would be with a plus, so it's 2 rhk divided by n, and minus h square k square n square. Am I right? That's vk. 2 pi equals to h and h, so let me just open it up. So it's pi, so it's 2 pi r h square k divided by n square, right? N and n. Correct? Correct. Minus pi h, and h square is h cube, k square divided by n and n square n cube. Do I have the same? Yes. Okay, this is my volume of the case cylinder. Now in my notes I have all these formulas, so but I would like to present the calculations. I mean, they're not very difficult, just have to be very accurate. Now I have to summarize it by k. Now when I summarize it by k, that's what? Sigma vk equals to, sum of these is 2 pi r h square divided by n square sigma k minus pi h cube. Is it h cube? Yes, h cube. Divided by n cube sigma k square. Right? Because these are constants, they're not dependent on k. That's why I put sigma only here. And summation is obviously from 1 to n. From 1 to n and from 1 to n. Now I will use something which I basically derived before more than once, namely this is equal to n times n plus 1 divided by 2, and sum of squares is equal to n plus 1 to n plus 1 divided by 6. Now I derived these both formulas in previous lectures. Now this is trivial. Whenever you want to summarize numbers from 1 to n, you just put underneath the sum from n to 1. And how to obtain this formula? Again, whenever I was talking about pyramids, I believe, yes, the volume of the pyramids, I actually derived this formula. So you can take a look at that lecture. So that's what I have. And I will substitute these two values here and here. And that would be my total volume of the cylinders. Alright, so volume of the cylinders equals 2 pi r h square divided by n square times this n plus 1 divided by 2 minus pi h cube divided by n cube. I hope you're not scared by these formulas, right? I mean, you have to do it, that's it. Times sigma of k square, which is n plus 1 to n plus 1 divided by 6. Alright. So all I have to do now is, well, simplify it maybe a little bit, and check what happens if n goes to infinity. Okay, simplification. Well, 2 goes with this, n goes with n square. So the limit of this piece, as n goes to infinity, n plus 1 divided by n goes to 1, obviously, right? N plus 1 divided to n goes to, well, it's equal to, for obvious reasons, if I divide it, it's 1 plus 1 over n, and it goes to 1 as n goes to infinity, because this goes to 0. So from this thing, I have only pi r h square. Pi r h square. Everything else goes out. Now, in this case, let's think about it. Again, the most important part, if you will multiply all these, would be 2n cube plus something n square, etc. So if you will consider this piece, it would be 2n cube plus something n square plus etc. divided by 6n cube. So what's the limit of this? Obviously it's 2 over 6, which is 1/3, and everything else would be down to 0, right? Goes to 0. So it would be minus pi h cube times divided by 3, right? 2, 6, that's the most important. Everything else would be would go to 0 as n goes to infinity. I think that's what it is. Let me just maybe simplify it a little bit. Let's say pi h squared divided by 3, and I will have 3r minus h. Is that right? Yeah, right. So that's the volume of the spherical cap, whereas r is the radius of a sphere and h is the height of the cap. Okay, now in the next lecture I will introduce another geometrical object, which is called spherical sector, and using that concept and using the volume which I have just derived, I will derive the volume of the spherical sector and then the area of the dome, and I will tell you how to do it. But anyway, today's purpose was to derive this formula for the volume of the spherical cap. I think a very good exercise would be if you just repeat all these calculations just by yourself. You know, you have to be accurate, you have to be disciplined, etc. So I think it's a very good exercise. So that's it for today. Thank you very much and good luck.